Consider the probability of error, that is MSK PSK, is given by P is equals to approximately, that is 2 into Q into square root of 2 E by N naught into sine pi by 4b. This is because we are calculating using the distance equation. This is the distance equation we are written here, that is 2 ES sine pi by 4. So ES can be changed as a 2 into ES can be changed as a 2 E by N naught. And next is the power spectral density of the MRI PSK. Here in the power spectral density, now the main thing we need to calculate the symbol duration. It is the symbol duration of the MRI PSK is defined by, that is T is equals to TB into log base 2m. Here where TB considered as a bit duration. And next is the baseband power spectral density of an MRI PSK is given by SBF of F is equals to 2E sinc sine square TF, sine square TF, and this can be written as in 2E can be written here. So therefore 2EB into log base 2m into, that is sine sinc square can be written as a sine square TBF into log base 2m, because this T is can be written as an here TB into log 2m. So this TB can be changed as a TB log 2m. Here F is same here, so same we are written in the F here also. Therefore this power spectral density of this can be given by n, that is the baseband spectrum of the power spectral density of an MRI PSK is given by 2EB log base 2m into sine square into TBF log square log base 2m. Next is the power spectrum. Consider the power spectral density of the MRI PSK signals. Consider here the M is equals to 2. How the signal varies, that is at 0 the value will be, that is the normalized power spectral density is given by 0.1 like this. That is for 0 it values minimum here. And next, for when M is equals to 4, at 0 we will get a normalized power spectral density as a 2. At M is equals to 8 we will get a normal power spectral density as 0 to the 3 points, that is at the value 3. These are the way, that is it ripples at a 0.5 here, goes like this, that is it reduces. First at 0 the frequency will be, that power spectrum is very high. When we are increasing the frequency, the power spectral density also decreases here. Next is consider these are the, that is M is equals to 2, M is equals to 4 and M is equals to 8. How it reduces the signal. And next is consider the channel bandwidth is required to pass an MRI PSK signals through an analog channels, as B is given by B is equals to 2 by T, that is 2 times of bit rate we are calculating, that is bit rate RB is given by 1 by TB. This is general, RB is equals to 1 by TB. Therefore the bandwidth in terms of bit rate we can be written as here B is equals to 2 RB by log base 2m here. And next the bandwidth efficiency of the MRI PSK is given by rho is equals to RB by B, where here rho is equals to RB is written by n that is log base 2m by 2, because we are we know that is how the 2 is given by RB by B. So we are written, that is RB is equals to RB. Next B can be written as we know 2 RB by log base 2m. So 2 RB by log base 2m, RB get cancelled. So next is 2 log base 2m goes here. This is rho is equals to 2. And consider if m is equals to 2, therefore rho is equals to log base 2m by 2. Therefore we will get an answer 0.5. And next is the bandwidth efficiency for for MRI PSK signals. Here consider the m bits per s by hertz, and for m is equals to 2 we will get in 0.5 like that. For m is equals to 4 we will get in 1. How? Because how like this is log base 2. Here wherever m is there, we calculate as m as active. M value is equals to 4. We will get a bit error rate. Bit rate is a 1, and for m is equals to 8 we will get 1.5. For m is equals to 16 we will get 2. For m is equals to 32 we get 2.5. For m is equals to 64 we will get 3. These are the table, that is the bandwidth efficiency of the MRI PSK, how we are calculating, that is using the log base 2 n by 2 formula. The MRI quadrature amplitude modulation, that is MQAM. Here the MRI PSK system, we are considering of an in-phase and the quadrature of the modulated signals, that is it results in an envelope constant in the remain constant here. How we are that is modulating two signals, that is in phase and out phase. If constant is removed as to permit in phase and the quadrature component are independent here, therefore the new modulation scheme has been introduced, that is called as an MRA QAM. Here in the MRA QAM, two dimension which involves two orthogonal basis function, passband basis function, that is phi 1 of t is equals to square root of 2 by t cos 2 by fct, and phi 2 of t is equals to square root of 2 by t sin 2 by fct. And let's consider the d mean, that is the minimum distance between the two message signals in the QAM constellation. Then the projection of the ith message point on the phi 1 and phi 2 axis are defined by the AI DIM by 2 and BI DIM by 2. Here I values takes the values between 1 to up to m. Therefore d minimum, that is d min by 2 is equals to square root of E naught, where E naught is the energy of the message signal which the lowest amplitude. And next is the transmitted MRA QAM signal. For the symbol K can now be defined in terms of as K SK to the power S of SK of t, that is given by 2 square root of 2 into E naught by t, ak into cos 2 by fct minus square root of 2 into E naught by t, bk into sin 2 by fc of t, where t goes values between 0 to t and k goes values between 0 plus or minus 1 plus or minus 2, like that. Therefore here we are considering the two things, that is the quadrature as well, in phase and quadrature. This is A is the in phase and B is the quadrature. The signal Sk of t involves the two phase quadrature carriers, which one of which is modulated by the set of the discrete amplitudes, hence the terminology goes the quadrature amplitude modulation. Here we are considering the set of, that is discrete amplitudes, we are considering the discrete amplitudes, therefore we will consider the quadrature amplitude modulation. We are considering mainly the amplitude. And next go for QAM square constellation. Next is the QAM square constellation. This can be given consider with an even number of bits per symbol. Therefore, we can written as an L is equals to square root of m, where L can take the values of a positive integer. And under this condition, that is the QAM square constellation can be always used in the Cartesian product of an one-dimensional L array. This is a Cartesian product of an ML one direction of one-dimensional L array PAM constellation with itself. By definition, there is the Cartesian product of the two set of coordinates representing the one-dimensional constellation, that is made up of a two set of possible orders of the coordinates within the first coordinate in each such pair, that is taken from the first set of product, and the second coordinate taken from the second set of the product, and thus the ordered pair of the coordinates naturally form a square matrix. This is given by them generally, that is ai comma bi square given by minus l plus 1 comma l minus 1 and minus l plus 3 comma l minus 1, and like that l minus 1 comma l minus 1. We close the bracket, and next is the minus l plus 1 comma l minus 3 and minus l plus L plus 3 comma L minus 3, like that L minus 1 comma L minus 3, and next is minus L plus 1 comma minus L plus 1, and minus L plus 3 comma minus L plus 1, and minus L minus 1 comma minus L plus 1. This is a general, that is the ordered pair of coordinates naturally form a square matrix. And consider this is an M array QAM for M is equals to 4, that is A1 that is phi of one axis the vertically oriented, and phi of two axis the horizontal oriented. Next is the vertical, that is phi 1 of t axis the vertical oriented, and phi 2 of t is the horizontally oriented. Look at this in the constellation, that is this is the phi 1 of t, it's in horizontally oriented, and phi 2 of t is the it is the horizontal oriented, and phi 2 of t is the vertical oriented. Next is this is a vertical horizontal constellation, and this is horizontally oriented constellation. This is given by here at a value 0 0. For 1 0 the value is d by 2, for 1 1 3d by 2, and 0 0 minus d by 2, 0 1 minus 3d by 2. Because m is equals to 4 means there are only 4 possible combinations, that is 0 0 0 1 1 0 and 1 1. For 0 0 the value will be minus d by 2, 1 0 for 0 1 value will be minus 3d by 2, and 1 0 is dv by 2, and 1 1 is 3 db by 2. And next consider this is in horizontal, that is phi 1, where in the vertical we can call it as a phi 2, and here also same, that is 0 0 0 1 1 0 1 1. For 0 0 the value will be minus d by 2, and 0 1 the value will be minus d by 2, and 1 0 the value will be d by 2, and 1 1 the value will be 3d by 2. Looking at these we are considering the that is here we are considering two-dimensional structure of M array. Here point should be in mind, keeping this point, that is following point should be considered as the same binary sequence issued for the both 4 array PAM constellation, and here the same binary sequence is used for both P array for both PAM constellation, that is same binary sequence we are using. And next is the gray encoded rule is applied here, which means that the as we move from one code to the other to an to one code word to an adjacent one, only single bit is changed here in the gray coding. And next is the constructing the 4 array M array constellation, we move from the one quadrant to the other clockwise, other one quadrant to the other clockwise direction, other counterclockwise direction. Here we move from the one quadrant to the other counterclockwise direction. Here we are moving from the counterclockwise direction, and next we are considered as with 4 coordinates. The 4 stages of the are given by the first quadrant. As we know that the first quadrant constellation is, if we use the code word along with the positive parts of the phi 2 and phi 1 of k, these values we are considered, that is 1 1 1 0 and 1 0 1 1. This comparison, that is top to bottom, left to right. Here top to bottom is nothing but I consider here this figure, that is from top to bottom and left to right here. So from consider this is center point. Here from top to bottom is nothing but a 1 1 and 1 0, and next here left to right. Here from left to right consider this is 2, that is 1 0 1 1 from center point. If we multiply these two, we will get a first quadrant, that is 1 1 1 1 into 1 0 1, that is like this 1 1 1 0 first quadrant, and next is 1 1 1 1 here, and 1 0 1 0, and next here 1 0 1 1. This is the first quadrant, and for the next second quadrant we get a top to bottom and left to right here. Same thing, top to bottom here the value will be remaining, that is 1 0 1 0 1 1 1 0, and from left to right here, left to right is, that is 0.01 0 0, consider in the second quadrant. So if you multiply, same thing, 1 1 0 1 and 1 1 0 0, that is this and this and this and this and this to this to this 1 0 0 1 1 0 0 0. This is a second quadrate constellation. To get in third quadrate constellation, same thing we are using, that is from top to bottom and left to right. Here from center point 0 to down, here we are using, that is 0 0 0 1 and here 0 1 0 0. This is the third quadrant we are using. Same thing, these values we will get. And for fourth quadrant we will consider the top to bottom and left to right, same here also. If we multiply these two, they will get these values. So these signal constellation of M array for M is equals to 16, how we can be written is nothing but look at this is the first quadrant. These values are written in the first quadrant and these values are written in the second quadrant. These values are written in the third quadrant and these values are written in the fourth quadrant. This is the signal space diagram of an M array QAM, that is M is equals to 16 with respect to, this is the two dimensions here, consider, that is phi 1 and phi 2. And next consider the